morning to all of you. In the previous class of ray optics, we have discussed about the scattering of light, and we come to know what is scattering of light and what are its different characteristics. Today we are going to discuss the most important topic of ray optics, and from the final exam point of view, that is microscope. Microscope, you know what is a microscope? Microscope is an optical instrument which is used to see a smaller object largely. That means if we want to see a very small object largely, then we use the microscope. This is called microscope, optical instrument that is used to see a smaller object largely. In your class 12 standard, in this particular chapter, we'll study microscope by classifying as simple microscope and compound microscope. So today first we'll go by simple microscope. So our topic is microscope. You kindly note down the definitions of microscope. Microscope, and we'll have two types of microscope we'll study. That is, one is simple microscope and the other is compound microscope. Simple and compound microscope, these are the two types of microscope we are going to study in your this particular chapter. That is a simple microscope and a compound microscope. I have told you the definitions of microscope. You please note down. The microscope is an optical instrument. Microscope is an optical instrument. Optical instrument that is used to see a small object largely. Okay, that is used to see a small object largely. That is called microscope. And now we'll discuss the simple microscope, and then we'll go to the compound microscope as well. You write down simple microscope. Simple microscope. So what is simple microscope and how a simple microscope is formed? That in a simple microscope we'll consider a simple convex lens. Okay, we'll consider a simple convex lens whose focal length is less but power is more. That means we'll consider a simple convex lens, and we'll place the object in such a place from where we can get a large image. Am I clear? So we know that in a simple convex lens, if we keep the object between optical center and principal focus, then we can find an enlarged image. Am I clear? So in this case we'll use a simple convex lens. Let's go for the ray diagram of simple microscope. If I consider that this is a here it is, this is a convex lens, simple convex lens, that is we have considered, and then we'll have the normal as well. This is normal of this particular lens. Okay, so this is suppose optical center. This is optical center, and this is focus. This is principal focus. This is suppose it is f1. This side will be f2. This is f1. This is f2, and gradually it will be go by twice f1, twice f2. The ray diagrams case you do all this thing. Now, as I told you that we need to produce a large image. That means we want to see a small object largely. That means the same way, in this case, we have to produce a large image of the object. I mean, for that we'll keep the object right at between optical center and the focus f1. So if we do that, then what will happen? This is the first ray that will come parallel to principal axis, and after refraction this ray will be passing through the principal focus. I have placed this, and this is f2. Understand? Now the next ray that will be passing through, the next ray that is passing through the optical center, the ray that is passing through optical center, it will undeviated. That means it will go undeviated. It's went this way and it will go this way. Understand? And now as you can see, there is no chance of intersecting between these two lines. That means they are not going to meet at any particular point. Okay? If I modify this diagram a little bit, nothing has been changed, just I have made a little modification. Okay, so in this case, what I can see, this is passing through the f2. Remember, this is passing through the f2. So they are going to meet in a specific point. If I extend them backward, and there's the image is going to form, and they're going to meet in some point like that. Okay, so this is the image produced by the object AB. So if I consider that object is AB, this object is AB, and the image will be what? Adis bidis. Image will be adis bidis, because object has been produced in the same direction as the image is produced in the same direction as the object is. So this is the ray diagram in order to understand in order to derive the magnifying power of a simple microscope. Remember, we need to find out the magnifying power of a simple microscope in this case. So if I move further for this particular topic, object, we have considered first of all a simple convex lens. Then the object is placed between optical center and principal focus, and the rest is, as you know, and the image is formed at A dash B dash. That means image is forming beyond f1. Image is forming between f1 and twice f1. So if I give this is twice f1, so image is forming right here. Am I clear? Now question is, when our purpose is what? Our target is to see this object clearly. That means we have to see a smaller object largely. When our human eye can see an object distinctly, that means at what distance our human eye can see an object distinctly, and that is at a distance of 25 centimeter. That means if the distance between the image and human eye is 25 centimeter, then we can see the image clearly, or we can see that particular thing distinctly. That means this 25 centimeter distance is called least distance of distinct vision. That is called LDDB. What is LDDB? LDDB is the least distance of distinct vision, where we can see an image clearly, or where we can see the image of an object clearly. That is called least distance of distinct vision. And for that, the image should be produced at 25 centimeter away from the human eye. So you can write down, this is LDDB, LDDB. This is called least distance for distinct vision, and that is 25 centimeter for normal human eye. That means if the image of an object is formed at 25 centimeter, then we can see that image clearly. Now, as of now, we'll consider that this is the image of the object. We'll consider that this image has been produced at LDDB. That means this distance is going to be your least distance of distinct vision, that will be expressed as capital D. Do you understand now? This distance from optical center to the image, this particular distance is going to be your least distance of distinct vision, that is 25 centimeter. That means we have considered that the image has produced at least distance of distinct vision, so that we can see the image of this object clearly. Am I clear? So you please note down this abbreviation of LDDB. Least distance for distinct vision is 25 centimeter. What do you mean by it? That means we can see the image of an object clearly at 25 centimeter distance from the human eye. Okay. Now, as I told you that in this case, what we need to find out? We need to find out the magnifying power, not magnification. Magnifications of lens you have got, that magnifications of lens was height of the image by height of the object. But in this case, we will find the magnifying power or angular magnification. And you will be asked to find out the angular magnification or magnifying power, capital M, in case of simple microscope. And in case of compound microscope also, the thing will be same. So if I write here that, or we'll find now that magnifying power now, magnifying power is also known as capital M, angular magnifications. You please note down, or angular magnification. So this is how we derive this particular thing. Magnifying power M is equal to, you can write that there is a definition of it. Magnifying power capital M will be written as the angle formed by image. That means this is the image, and image is forming an angle with the optical center. With the optical center means I am considering that the observer's eye is attached with this particular lens. That means observer's eye is exactly attached with this particular lens. That means observer will see from this particular point, and then he will see that this is the image, and there will be some amount of angle. Then angle formed by object when it is at LDDB. That means we are supposing that the object is placed at least distance of distinct vision. That means we are going to find out that what will be the magnifying power of the simple microscope once we keep the object at least distance of distinct vision. That means we'll see the image now by keeping this object at least distance of distinct vision. Is it clear to all of you? No need to get confusion. Simply angle formed by image, that one angle will be formed by the particular image, divided by the angle formed by the object. That means object will be placed at least distance of distinct vision. Am I clear? Now, if I consider that these images are, suppose this is the object AB, At the beginning where the object is placed between optical center and the principal focus. Am I clear? But this time we need to find out the magnifying power, and we are finding the magnifying power by keeping the object at where least distance of distinct vision. That means we will transfer this object to least distance of distinct vision, supposed to be here. Suppose this object is C. B dash C. Now B dash C is the object AB. B dash C, the object we have kept now at least distance of distinct vision instead of between optical center and principal focus. So what will be the case now? If I consider that this was the image and this image has formed angle, suppose this angle is supposed to be beta. Beta is the angle formed by the image, and then there will be one more angle will be formed by the object. Okay, suppose this is the image angle formed by the object, and this is alpha. So this is alpha. Alpha is the angle formed by the object that is placed at least distance of distinct vision, and this is beta. This is beta, and this beta angle is formed by the image with respect to the optical center. That means where the human observer's eye is attached. Is this point is clear to all of you? So we can write that in this regard m is equal to we can write we'll write angle formed by image. This is the image, and images form an angle beta. Okay, and the angle formed by the object where it is placed at LDDB, that means this is alpha. So we can find that magnifying power m is equal to alpha by beta. Now one more thing, if we consider that if the angles are too small, if the angles to be too small, then we can write that this beta will be equivalent to tan beta and this alpha will be equivalent to tan alpha. So I can write, since the angles are too small, as you can see here, if the angles are too small, if angles are too small, which angle? These angles. If angles are too small, then we can write that alpha will be equivalent to tan alpha and beta will be equivalent to tan beta. Am I clear? That means this time we can write, therefore m is equal to tan beta by tan alpha. Can you get it? Okay, why I have written tan beta and tan alpha? Since this, and if angles, these angles if I consider to be very small, then I can write that alpha will be equivalent to tan alpha, beta will be equivalent to tan beta. So this will be transformed to m is equal to tan beta by tan alpha. Is that clear? So this is your magnifying power tan beta by tan alpha. Now the next case. In the next case, if I want to find out the tan beta and tan alpha respectively, that means I can find out tan beta. This is beta. This beta I can find from this particular triangle also. Finding out the beta from triangle AOB or AOB is quite similar. That means I can find the tan beta from the triangle AOB also, as well as I can find out this angle alpha, tan alpha, from triangle COB. That means I can find beta, tan beta from triangle AOB, yes, and tan beta I can find from the triangle COB. Okay, so I will write, therefore m is equal to, in this case, therefore m is equal to, in the place of tan beta, this is tan beta, this is beta, this triangle is beta, this angle is beta, and this beta I will find out from the triangle AOB. Okay, triangle AOB. What is that? I mean, how to find the tan theta of a triangle? Perpendicular upon base. So here this is perpendicular AB, and OB is the base. So AB by OB I can write. In the place of tan beta I will write AB by OB into. Have you got it? This is AB. AB is the perpendicular and OB is the base. So tan beta is coming AB by OB. I have derived tan beta from this triangle AOB. I have find the tan beta. Next, if I go to find the tan alpha, this is tan alpha. Tan alpha I can find from the triangle COB. This is triangle COB. Now if I try to find the tan beta alpha from here, then this is in triangle COB, CB or B C by OB. I can write what? CB by OB, but this ratio as I put in here, this will become reverse. So in the place of tan alpha I can write this is OB will go up and CB will come down. So this is OB by CB. Understand now? This is very simple thing. It is a mathematical analysis. Tan beta perpendicular upon base, tan alpha perpendicular upon base, but once I change the ratio, this will become reverse. That means this implies if I continue in this side, M is equal to, as you can see here, this is AB and CB dash. This is AB is the object and this object is in place at CB dash. That means AB and CB dash are similar, so I can cut AB and CB dash. So M is equal to, we can write here OB dash by OB. Is that clear to all of you? This AB is also object and CB dash is also object. As you can see here, this AB and B dash C or CB dash, they can be cut down because they are similar. So what is left for me? That means as I have got, therefore M is equal to, what is OB dash for you? This is OB dash. OB dash was your D. That is least distance of distinct vision, but this will be minus because this is left of against the incident ray. So this will be what? In the place of OB dash I will write minus D. Have you got it? This is OB dash. In the place of OB dash I can write minus D because this is least distance distinct vision we have already considered. Next we will have OB. What is OB? This is OB. This is OB. OB is the object distance, and similarly this is also going to be your minus. Okay, so we can find that M is equal to, that means M is equal to D by U. Understand? M is equal to D by U we have got, and this M is equal to D by U, this is the general magnifying power. M is equal to D by U, this is the general magnifying power for the simple microscope. Understand now? So how we have find it? There are some mathematical ratio. These are, you also can, if you practice, this will become easy for you. Just simply you have to get the concept right here. Okay. Next, this is M is equal to D by U. As I told you that this is the magnifying power for general setting, general magnifying power formula for the simple microscope. But now here two possibilities arise. If I consider this times, now if I consider, suppose as I told you, if the image is at LDDB, if the image is at LDDB, then what will be the magnifying power of this particular compound simple microscope? Have you understood it? This is the general things. M is equal to D by U. We have got it. But if the image is at least distance of distinct vision, if we found the image is at least distance of distinct vision, then what will be the magnifying power for this particular simple microscope? Now we'll find out. Now for this we have to bring the lens formula here. We know from lens formula from Lenz's formula. What is Lenz's formula? From Lenz's formula we know that 1 by f is equal to 1 by v minus 1 by u. This was your Lenz's formula. So now I want to bring this d by u in this particular Lenz's formula. So what I can do now, that once I write this 1 by f, that 1 by f, the focal length, since this is convex lens, this focal length is going to be your positive. This is equal to 1 by v. What does v? V was image distance. Image distance was, this is OB dash, and image distance we have kept where the image is at LDDB. That means this is image has been at least distance of distinct vision. That means we can say that in the place of v I will write minus of d. So this is minus of d minus 1 by u. U is itself minus. If I put the value of u here, if I sign convention I used, then this object distance u will be minus, so minus minus plus 1 by u. Now if I multiply both sides by d, now I am going to multiply both sides by capital D so that I can bring these things here. So if I multiply, this will be d by f is equal to minus 1 plus this is equal to d by u. Okay, I have multiplied by d by f minus 1 d by u. Similarly, I can see now if I bring this particular things here, so we can write that d by f plus 1 is equal to, in the place of d by u I can write as m. Am I clear? So we can write that magnifying power for a simple microscope when the image is at least distance of distinct vision can be found as m is equal to 1 plus d by f. This is something more important to know for you. Remember, this was general, this is normal magnifying power for a simple microscope. M is equal to d by u, and when the image you consider at least distance of distinct vision, then m is equal to 1 plus d by f. Okay, this is number one possibilities. Now one more possibilities can be arrived. If you go for a normal setting of the simple microscope, that means if you go for a normal setting, means what? The image is at infinite distance. Distance we have considered that image is produced at least distance of distinct vision. Then what we found that m is equal to 1 plus d by f. But if we consider that image is produced at infinity, so what will be the situation? If I write second case, if image is at infinite distance, image is at infinite, okay, image is at infinite distance, then what will be the magnifying power of simple microscope? So if the image distance is infinite, so if image is produced at infinity, so this object should be placed at focus. If we keep the object at focus, object should be placed at focus, then will be the image will be produced at infinity. So from Lenz's formula in this case also, from Lenz's formula what we know, 1 by f is equal to 1 by v minus 1 by u. In this case we can write 1 by f is equal to this 1 by v, where image is produced, image is at infinite distance, so it will be 1 by minus of infinity, image distance will be negative as well. Okay, image is produced this side, then this is object distance, it is plus 1 by u. Again the same thing, I will go for it. So I will multiply both sides by capital D as I did here. So this will be d by f, this is 1 by infinity is going to be 0, so this is d by u. That means I can write in the place of d by u, this is m is equal to d by f. Understand? So this is one more equation, that if the object image is formed at infinite distance, then this will be the magnifying power, m is equal to d by f. This is for maximum case, and this is for minimum case, because if the image is produced at infinity, we'll see the image is very small. That means this is for maximum case, this is for maximum case, and this is for minimum. Okay, this is for minimum, but you need to understand the point. Now total we have got three magnifying power for simple microscope. The first is, this is general, m is equal to d by u, and this is m is equal to 1 plus d by f, that is maximum magnifying power. And when this arrive when we keep the object at image at least distance of distinct vision. Once you keep the object at image, once you find the image at infinite distance, then this is m is equal to d by f. I hope you have understood all these things. This is a very important topic for class 12 physics. Please practice, go through it. If any doubt, just inform me. We'll try to clear the next class again if you need. Thank you so much.